Hey Akash, this one's for you, I guess. This is 7.11 on, so this is on page 257. It's one of the practice problems. Unfortunately, the examples you gave me were not so good. The reason why is because none of them have lone pairs. So I guess if you could find me one with lone pairs, that would be great. Anyway, the first one, so we're going to find out what the VSEP, what kind of geometry do we think these molecules have using the VSEPR method, okay? So in this, the first one, for example, this is 7.11 right now, okay? For A, we have, this is mercury bromide, but actually no, this is mercury dibromide, okay, dibromide. We know that because this is a covalently bonded, molecule, okay? So the first thing I do is I know that mercury is the least electronegative of these, okay? Keep in mind your trend. If you have a periodic table that looks like this, and I can't draw staring at my iPad, it'll go to the top right. For the most part, it'll go to the top right in terms of your trend of increasing electronegativity. So I always look for the NOF. In biology, a lot of times you'll see that these three are going to be, oxidizing everything. They're going to be stealing electrons from things. And that's because they're very electronegative. They really just try to pull away electrons within a bond. And keep in mind that when you're talking about electronegativity, you're talking about a bond. You're talking about electrons that are shared in a bond, but where in that bond do you see the electrons kind of closer to? Do you see them closer to the mercury or the bromide? Okay, so in these cases, if I were to draw a dipole moment, they would be going out this way. Okay, so anyway, the first thing I would do is I would draw my Lewis structure. Okay, so my Lewis structure here, I will have 12 electrons. Okay, the way I did that, I have 14 from the two bromides. I add 2 for the mercury. Okay, now mercury is kind of a transition. I believe it's a transition metal, and so you might be tricked out by the D. Okay, because it has a full D orbital. But keep in mind that on the periodic table here, even though mercury is here, well, that D officially is actually whatever period this is, I guess it's the 5th period, okay? That's 5D, okay? That's 5D10. It's not 6D10. It's not actually a valence electron, okay? So you don't have 10 valence electrons on top of your S's. You actually only have the 2 whatever electrons are in your s orbitals, that's your 6s, okay? So because mercury has something like 6s2, 5d10, okay, you're only going to have these 2 electrons. So that's going to be your 2 electrons here, okay? So then you add those together, you get 16, you have 4 in your bonds, so that's 12. So then I'll put my 12 electrons on my 2 terminal atoms. And again, this would be better if I had lone pairs, okay? The reason why is because in all of these examples, because we don't have lone pairs, our electron domain geometry and our molecular geometry are going to be the same. So here we only have 2. Actually, hold on, I screwed this up, didn't I? I believe I screwed this up by accident. So I should be completing an octet here. So actually I should have a double bond here. Take that away. And a double bond here. Okay, so I screwed that up. This might still be wrong, so do not take this for a word, but for the most part, just listen to what I have to say about the electron domains, which is that you have 2 electron domains here. When you have 2 electron domains, it should be linear in your electron domain geometry. Here, it's... Hold on. Oh, bless me. Anyway, my molecular geometry is going to be the same, because I have no lone pairs. Okay? Now, down here, I've got SCN. So this is thiocyanate, okay? I have a -1 charge. So what I do usually is I write the SCN. The C is my center atom, okay? I know this because it is the least electronegative of these, okay? A kind of unfaithful rule of thumb that I've been using, but double-checking by using my periodic trends for electronegativity, is that what I would do is I would say, okay, well, carbon can create 4 bonds, sulfur can create 2, nitrogen can create 3. Because carbon can create more bonds, it's going to be in the middle. Now, that's not always going to work, I think, all right? But for me, that's just been my little trick, but don't rely on it, okay? So anyway, here's my carbon. Once again, I'll add up all of these different, the different amount of valence electrons, and I'll add 1 because I have a -1 charge here, okay? So I'll get 16, I'll subtract 4 for the bonds, And then what I did there is then I had to complete the octet for carbon, so you have 2 double bonds here. So I have no lone pairs, as you can see on carbon. It's completely nice and happy with its 2 double bonds. So I have 2 electron domains. Okay, even though I have double bonds here, this isn't 4 electron domains because a double bond counts as only 1 domain. Okay, so it doesn't matter if I have a single bond or a double bond here. That's 1 electron domain. Okay, so that means that I have linear because there are 2 electron domains. And likewise, I have no lone pair, so I know my molecular is also linear. So I wanted to send out another example. This also doesn't have any lone pairs, but and I didn't balance this. Okay, it should be like this. Okay, I forgot to put on the double thing there. Anyway, this could be wrong. Again, it's late, so I'm a little tired. But anyway, NO3, this is nitrate. Okay, this was one of our polyatomic ions. Once again, I add up everything. I added 1 for the charge, and I subtracted 6 for the bonds. Okay, I placed down my 18 valence electrons. Okay, and then I shared 1 with this oxygen. Okay, to the nitrogen, so that way the nitrogen could fulfill its octet. You're going to see resonance structures, yes. So you're going to have another equivalent resonance structure with the double bond here, and there's a single bond here with 4 electrons, kind of 2 lone pairs out here and 3 out here, and then likewise a third structure is going to have your double bond here instead, and all 3 of those contribute equally to the resonance hybrid, but I'm just going to use one of these. Okay, so I have 3 electron domains here. Okay, so 3 electron domains with no lone pair. So the first thing, it doesn't matter how many lone pairs I have, it just matters how many electron domains I have. Trigonal planar, okay, because I have 3. Okay, but because I have no lone pairs, I would have trigonal planar. Now let's say we live in another universe, okay, where we have a lone pair here for some reason. Okay, obviously this doesn't balance out, it's not right, but let's just do this for the sake of learning. Okay, what we would have is we have a double bond here, single bond here, and a lone pair. So we have 1, 2, 3, 4. We have 4 electron domains here. Okay, so officially we should have a tetrahedral on our electron domains. But because we have a lone pair there, what we would see is a tetrahedral. Let me draw this first. Okay, so I'm just going to draw the shape out as we've learned how to look at it. Okay. But what we're going to do here is because we have 4 electron domains, yes, but one of them's a lone pair. So I'm going to replace actually this top part here with a lone pair, okay? The reason why, you want to maximize your angles. You can see that this angle here is greater than this one here. So why would it replace one of these with a lone pair? It would replace the top one with a lone pair, okay? I mean, it could replace this one, but actually, it could replace any of these and would still be the same shape. It's just a matter of the orientation of how you're looking at it. But you can see how this forms kind of a pyramid, okay, shape. Okay, this would be in 3D, obviously. So we call this trigonal pyramidal, or pyramidal. Trigonal pyramidal. That would be your molecular geometry.